So in the last class we've seen the relations connecting Young's modulus, bulk modulus and the Poisson's ratio sigma. Today we will be seeing the relation connecting Young's modulus, rigidity modulus and Poisson's ratio sigma. Now again consider a cube here with the upper face A, B, E, G as you can see in the figure. Now a tangential force is applied along this surface with the base of the cube fixed on the surface. Now this tangential force causes the upper surface to shear through an angle theta, and the corresponding displacement A dash caused by this tangential force is L, small l, or this length B dash is also small l, and theta is the shearing angle. Now when this shear happens, or when we apply this tangential force along the upper surface, the diagonal dB changes to dB dash, which is greater than dB. So dB changes to dB dash. Also the diagonal AC, which I have not marked here, but the diagonal AC changes to A dash C, which is shorter than AC. So we have an elongation along this diagonal dB, which changes to dB dash, and we have a compression along AC, which changes to A dash C. Now the strain produced, or rather before that, the tangential or the shearing stress applied can be written as force upon area. Force is the tangential force and area is the area of the face of the cube, which is L square, if capital L is the length of the edge of the cube. Now the strain produced can be written as theta equals small l upon capital L. Small l is the displacement caused by this shear. Now the tangential or the shearing stress is represented by capital T. Remember this. And the rigidity modulus now can be written as N equals, or eta equals, capital T upon theta. That is shearing stress upon shearing strain. Shearing stress is T and shearing strain is theta. And we can simply divide these two equations and obtain the rigidity modulus. Now, an important point to note is a shearing stress along AB is equivalent to a tensile stress along the diagonal DB and an equal compressive stress along the diagonal AC perpendicular to it. See, we have applied the tangential force along this direction. Now we are saying that this shearing stress caused by this force along the tangential direction along AB is equivalent to a tensile stress along DB. What is tensile stress? Tensile stress causes the elongation. So this tensile stress along DB and a compressive stress along AC. Compressive stress causes the decrease in length. So the new length of the diagonal is A dash C. So I'll repeat, the shearing stress or the tangential stress along the surface or the direction AB is equivalent to a tensile stress along DB and a compressive stress along AC. Now, if alpha and beta are the longitudinal and lateral strains per unit stress respectively. So alpha is the longitudinal strain per unit stress, and beta is the lateral strain per unit stress. We've already seen these terms in the previous class. Now, the extension along the diagonal dB due to tensile stress along dB. So when we apply this tangential force along AB, which causes the tangential or the shearing stress, we know this diagonal dB changes to dB dash. So there is an extension of dB, or there is an elongation of dB. So this elongation is caused by two factors. One, a tensile stress along dB, and the second factor is a compressive stress along AC. So the extension or the elongation in dB is caused by a tensile stress along dB and a compressive stress along AC. We've already seen that when we compress along AC, there will be an elongation along dB. So the extension along diagonal dB due to tensile stress along dB is given by dB into T into alpha, where T is the shearing stress or the tangential stress, and alpha is the longitudinal strain per unit stress. How did we obtain this term dB into T into alpha as the extension? We can just understand by these calculations that dB into T is the tangential or the shearing stress, which is force upon area, and alpha is the longitudinal strain upon per unit stress. Now the strain is the change in dimension to the original dimension. Let the change in dimension be delta dB, the change in dimension along dB be delta dB, and the original length is dB, and the stress is force upon area, and this force upon area terms can be cancelled, and the remaining term will be delta dB because dB and dB gets cancelled. So finally delta dB, which is the extension or the elongation or the additional length caused by the tensile stress along dB. So similarly we can obtain the extension along dB caused by the compressive stress along AC, which is dB into T into beta. You can verify this in the similar way like this. Now the total extension along dB will be the sum of these two terms, the sum of the terms which caused by the tensile stress along dB and a compressive stress along AC. So these two terms can be added, and finally we will obtain dB into T into alpha plus beta. You know dB is nothing but L root 2. If L is the side, this diagonal will be L root 2. L root 2 times T into alpha plus beta. Now if we draw a perpendicular BP from B onto dB dash, the increase in length in dB is PB dash. See, we know the new length of dB is dB dash, and if we just draw a perpendicular BP, so this BP is perpendicular to B dash D, then the length PB dash, this length is the additional length or the elongation caused in dB. So this is the additional length in dB. And if theta is very small, that is if the shearing angle theta is very small, we can take A, B dash, C as approximately 90 degree. Not exactly 90 degree, but can be taken as approximately 90 degree if theta is very small. If theta is very small and the angle A, B dash, C is 90 degree, then Angle B, B dash P can be taken as angle 45 degree. That is, if A, B dash C is 90 degree, we can take angle B, B dash P as 45 degree. Now, the increase in length in dB is PB dash. I've already said that the increase in length dB is PB dash, which is also equal to this length L, this length is small l, times cos of this angle B dash P. So you can write cos of this angle. We've already seen the angle B dash P is 45 degree. Now cos 45 can be written as adjacent side by hypotenuse. Adjacent side is P dash, hypotenuse is small l. So we can write the length P dash as L into cos 45 degree. So this will be P dash will be L cos 45 degree, which will be L into 1 by root 2 or L by root 2. So the increase in length of the diagonal dB is L into cos 45 degree, which is L by root 2. Now we've also seen that the extension, the same value or the extension along dB is also equal to this term, which we have already calculated here, is L root 2 times T into alpha plus beta. So we can equate these two terms. Equating these two terms, L by root 2 and this term, and finally after some simplification we can obtain the relation between rigidity modulus, Young's modulus and Poisson's ratio. So you can just verify this. Now we will see the relation connecting bulk modulus, rigidity modulus and Poisson's ratio. And from the previous calculations, we know Young's modulus Y equals 3K into 1 minus 2 sigma. We've already seen here that Young's modulus Y equals 3K into 1 minus 2 sigma. And from the calculation that we did in the just previous step, we know that Young's modulus Y equals 2n times 1 plus sigma. So using these two relations, we can equate these two relations because LHS is Y on both the terms. So equating the RHS, we will obtain the relation between Poisson's ratio sigma, bulk modulus K and the rigidity modulus N. Now we will obtain the relation connecting Young's modulus Y, bulk modulus K and rigidity modulus N. We know from these two relations 1 minus 2 sigma is equal to Y upon 3K, and from this 1 plus sigma is equal to Y upon 2N. So using those two relations, 1 minus 2 sigma, 1 minus 2 sigma equals Y upon 3K, and 2 into 1 plus sigma equals Y upon N. 2 into 1 plus sigma, which is equal to 2 plus 2 sigma equals Y upon N. So adding these two equations on the LHS, we will get 2 plus 1 3 and 2 sigma minus 2 sigma cancels, and adding these two terms on the right hand side. So finally we obtain the relation connecting Young's modulus, bulk modulus and rigidity modulus. Now limiting value of Poisson's ratio can be calculated from this relation 3K minus 2N, from this relation 3K into 1 minus 2 sigma equals 2N times 1 plus sigma. So from this relation we can calculate the limiting value of Poisson's ratio. Now if sigma is a positive quantity, then if sigma is a positive quantity, RHS should be totally positive. Right? If sigma is positive, this term should be positive anyway. If this term is positive, LHS should also be positive because LHS equal to RHS here. So to make this term positive, the only possible way is to make 1 minus 2 sigma positive. So 1 minus 2 sigma is positive, means 1 minus 2 sigma greater than 0, which means 2 sigma less than 1 or sigma less than 0.5. So which means the upper limit of sigma is 0.5. Now, if sigma is a negative quantity, first case we took the sigma as a positive quantity. If sigma is a negative quantity, sigma negative means this term becomes minus minus positive. So LHS becomes positive. If LHS is positive, RHS should also be positive. To make this positive, 1 plus sigma should be greater than 0. If 1 plus sigma is greater than 0, sigma should be greater than minus 1. So we got the lower limit of sigma as minus 1. So sigma should lie between minus 1 and 0.5. So these are the theoretical limiting values of sigma, minus 1 and 0.5. But practically in most materials, values of sigma lie between 0.2 and 0.4. So in this class, we have discussed the relations connecting Young's modulus, rigidity modulus and Poisson's ratio. Bulk modulus, rigidity modulus and Poisson's ratio. Young's modulus, bulk modulus and rigidity modulus. Thank you.